Hey there, Calc2 crew, and welcome back to the Daily Problem Sets. And today we're going to be taking a look at some material from Chapter 8. I'm going to talk about arc length and then area of surface of revolution. So first, with arc length, we have a familiar definition. Remember, you should already be watching the lecture videos before taking a look at these. Remember, we say if f prime of x is continuous on the interval from a to b, then the length of the curve y equals f of x for a to b is given by, and here we have a familiar formula, square root, we are integrating from a to b to find arc length, the square root of 1 plus, we have our derivative squared, and then with respect to x. Or of course we could use Leibniz notation if you prefer. And that would be the integral from a to b of the square root of 1 plus, here we have dy dx squared, and then integrating with respect to x. Of course, arc length doesn't really care if we're moving in the x direction or the y direction, so we could talk about dx dy and integrating with respect to y as well. And we'll see that in our first example. So here we'd like to find the exact length of the curve x equals y to the fourth divided by 8 plus 1 divided by 4y squared, and then we have bounds given on y from 1 to 2. And I like to use the bounds to give me sort of a bit of a push into one direction or the other. Since I'm given bounds on y, I would want to try to set up the integral with respect to y so that I can use these bounds. Moreover, if I look at my function, I can't really alter it. I wouldn't be able to solve for y explicitly. So we'd say, well, looks like it's ready to be used as an integral with respect to y. Let's find the pieces that we need. I do need my derivative, dx dy in this case. And if I differentiate, my coefficient 1/8 comes along for the ride. Derivative of y to the fourth gives me 4y cubed. And then here, think of this 1 over 4y squared sort of as 1/4 and then y to the power of minus 2 for that one term. So we'd say, well, the coefficient 1/4 comes along for the ride. The derivative of y to the power of minus 2 gives us minus 2 y to the minus 3. And then we can clean up this derivative a bit. So here we'd say 4 divided by 8 gives us 1/2 y cubed. Here I get a negative 1/2, and that's y to the minus 3. So this is what we get for dx dy. But what I want to do next is I want to square this. So I'd say, okay, well, dx dy, if I square it, since I have a binomial here, that means I really want to FOIL. So I might even just write it out twice, 1/2 y cubed, and then minus 1/2 y to the negative 3, and I want to multiply that by itself. I want to square it. And then here we can work through FOIL. We're foiling this out. So first, we'd get 1/2 times 1/2 gives us 1/4, and y cubed times y cubed gives us y to the 6th. For the outer and inner terms, and I'm going to get two of the same thing, I get 1/2 times negative 1/2 gives me a negative 1/4, but then y cubed times y to the minus 3 just sort of cancels. It gives me 1, gives me y to the 0, which is 1. But then I get another one of those same products. So I get a minus 1/4 and then another minus 1/4, which we can combine later. And for the last term on FOIL, negative times negative is positive. 1/2 times 1/2 is 1/4. Y to the minus 3 times y to the minus 3 gives us y to the minus 6. And then as promised, we said we could clean this up. So this is going to give us 1/4 y to the 6th, and then minus 1/2, and then plus 1/4 y to the minus 6. Now what we'd like to do is we'd like to throw this under the square root, but we also want to add 1 to it. So if I want to set up my integral now to find the arc length, I can. So we'd say here I want the integral, and my bounds were from 1 to 2 on y. So the integral from 1 to 2. And remember how our formula looks. Here we're doing it with respect to y, but it makes no difference. It should be the square root of 1 plus the square of the derivative. We just found the square of the derivative, so I just need the rest of this. Square root of, I want 1 plus, and then here's my derivative squared. It's that 1/4 y to the 6th minus 1/2 plus 1/4 y to the minus 6. And here we're integrating with respect to y, of course. Now I can add those constants together under the square root. So we'd say integral from 1 to 2, square root of, and then here I'll write this 1/4 y to the 6th term first. But 1 minus 1/2 gives me plus 1/2, and then plus 1/4 y to the minus 6, and then dy. Now this is where we start to run into a bit of a problem. We look at this, it looks very menacing, and we say, well, what could I do in this case? I want to integrate this. I have all this crazy stuff under the square root. How am I going to integrate this, right? And this is where we really want to we want to do some wishful thinking. We'd say, well, wouldn't it be nice if all of the stuff under the square root could be written as something squared, right? Because if I had the square root of something squared, well, let's just say smiley face squared, then the square root and the squaring is going to cancel, and that's just going to leave me with smiley face. And I would like to smile today. I'd like to be happy. So this would be great, right? If I could have the square root of something squared, then I could work with this a bit better. So, well, sometimes we just want to be the change that we want to see in ourselves. So let's see if we can't do this. And I want you to always believe in who you are, trust your instincts, follow your heart, of course. Let's see if we can't do this. I have 1/4 y to the 6th plus 1/2 plus 1/4 y to the minus 6. And I'm going to give you a little sort of pro tip, an insider tip here. If this is going to work, it's going to work practically effortlessly. So I would say try to factor this, and don't even sit there and stare at it and wonder, well, what should it be? Just think about it. Look at this first term. What would I square to get a 1/4 y to the 6th? Well, I think reasonably 1/2 times 1/2 gives me 1/4, and y cubed times y cubed gives me y to the 6th. So let's try a 1/2 y cubed. Let me look at the last term now as well. What can I square to get a 1/4 y to the minus 6? Well, 1/2 times 1/2 gives me 1/4, and y to the minus 3 times y to the minus 3 gives me y to the minus 6. Since I want the outer and inner terms to add up to something positive, that means I should really be putting a plus sign in between here. So what we're saying, or what we're sort of guessing at this point, is that hopefully this will factor into a 1/2 y cubed plus 1/2 y to the minus 3 quantity squared. And we can actually show that it works out. Now we've already checked on the first and the last terms of FOIL. In fact, that's how we generated this binomial here. But if I want to check the outer and the inner terms, I'll do that sort of scratch work here in the margin. That would be 2 times, because I get the same thing twice over, 2 times the product of these terms. So we're saying, well, the outer and the inner terms to check should be 2 times 1/2 y cubed times 1/2 y to the minus 3. And what does this give me? Well, 2 times 1/2 cancels, y cubed times y to the minus 3 cancels, so this just leaves me with a positive 1/2. And this is just for the outer and the inner terms of FOIL. We already know the first and the last terms are going to work out. That's how we picked these pieces. And certainly enough, I want that to be a positive 1/2. So yeah, so it worked. So everything is great then. Which means that we should be able to work through this. There's a light at the end of the tunnel. So the integral from 1 to 2 of the square root of, but all of that stuff under the square root symbol, we can actually write it as something squared. And I'm smiling because I'm happy. I'm very happy about all of this work that we're doing, the calculus, yes. So I can write this in. It's an integral with respect to y, and now the square root and the squaring are going to undo one another, so that I'm left with the integral from 1 to 2 of 1/2 y cubed plus 1/2 y to the minus 3. And now I can integrate, now I can evaluate and get that final answer. So for integration, we would say 1/2 comes along as the coefficient. Integrate y cubed to get y to the 4th divided by 4. 1/2 comes along as my coefficient. Integrate y to the -3 to get y to the -2 over -2. And this is from 1 to 2. And I'm going to clean this up a bit. So here I have y to the 4th divided by 8. And then minus, this is going to be a 1 over 4. And I'm going to bring the y to the -2 down in the denominator and make it a y squared. We like those negative exponents for calculus, derivatives, integration, stuff like that. But now that I want to evaluate and plug things into the functions that I have, the terms that I have, I think it's better written as a fraction. Now I want to evaluate, and that's all that's left, right? Plug in the upper bound, plug in the lower bound, and subtract in between. When I plug in 2 for y, I get 2 to the 4th divided by 8 minus 1 over 4 times 2 squared. I want to subtract away from this. When I plug in 1 for y, I get 1 to the 4th over 8 minus 1 over 4 times 1 squared. And we can work through this as much as we can. Now 2 to the 4th divided by 8 is going to give me 2. And here I get minus 1 over 4 times 2 squared is 4 times 4, which is 16. And then in my other parentheses, I'm subtracting away. I have 1 to the 4th is 1, so that's 1 over 8. And then minus 1 over 4 times 1 squared is 1 over 4 times 1, which is 1 over 4. Now from here, I'd want to bring the minus sign through, get rid of the parentheses. I should also get a common denominator. So here 2, if I multiply this by 16 over 16, that's 32 over 16, minus 1 over 16, and then here minus, if I multiply this by 2 over 2, gives me 2 over 16, minus a negative is plus. If I multiply this by 4 over 4, gives me 4 over 16. I can combine my like terms. I'm going to leave this first fraction alone. I'll come back to it. But here I have negative 1 minus 2 is negative 3, plus 4 gives me positive 1 over 16. And then I can finish adding. So I have 33/16. So not so bad. We'll take a look at one more example here for arc length, and then we'll move on to the next bit of material that we're sort of reviewing on. Find the exact length of the curve. Here we have y equals natural log of secant of x, and that's from 0 to pi over 4. This is going to be an interesting one. So here, I would say again, let the bounds be the motivation. I want to set this up as an integral on x with respect to x. So I should go ahead and start differentiating then. I want dy dx. I'm going to build my setup for my integral. The derivative of natural log of secant of x, I need to use chain rule. So first, the outer derivative, my outer function is natural log. Derivative of natural log of stuff gives me 1 over stuff. And the inner function is secant, so 1 over secant. But I'm not quite done, right? Remember with chain rule, we have to multiply by the derivative of the inner function. So I have to multiply by the derivative of secant. And the derivative of secant is secant tangent. So I get 1 over secant times tangent. I can clean this up right away because secant divided by secant is going to cancel. So in fact, my derivative just leaves me with tangent of x. We'd say we'll go ahead and set up to find the arc length. I want the integral from 0 to pi over 4 of the square root of, and I want 1 plus my derivative squared, so 1 plus tangent squared, and then with respect to x. Well, hopefully this looks familiar. This is actually a Pythagorean identity. If we remember, sine squared plus cosine squared equals 1. And excuse my poor notation, it should be sine squared of x, for example, cosine squared of x. Let me throw that in there so nobody makes fun of me. And if I divide everything through by cosine squared, so divide everybody by cosine squared of x, everybody, we'd say sine squared over cosine squared gives us tangent squared. Cosine squared over itself gives me 1, and 1 over cosine squared gives me secant squared. So here this is from an old Pythagorean identity, a new one. We'd say, well, tangent squared plus 1 is really secant squared. So I can go here and I can rewrite this and say, well, this is the integral from 0 to pi over 4 of the square root of secant squared of x with respect to x. And the square root of secant squared, we can reduce this and say, well, that's just secant. So here we have the integral from 0 to pi over 4 of secant of x with respect to x. So okay, so now we want to know, what is the antiderivative of secant? Well, that's not quite the easiest question, but let's actually take a look at the integral of secant, and we'll do this to the side here. My favorite thing to say, notice. Let's take a look at the antiderivative of secant of x. And to integrate secant of x, there's a few ways we could do this, but I think the best way to do it is with a very clever trick. And if you haven't seen the integral of secant yet or before, then I guess consider yourself lucky. What we would want to do is we would want to multiply this by a very elaborate form of the number 1. And just bear with me for a minute. I'm going to tell you what it is because I don't think it's obvious. We're going to multiply by secant of x plus tangent of x divided by secant of x plus tangent of x. Same thing on top, same thing on bottom, so it's just the expression 1 that I'm multiplying by, but this is going to modify what we have into something that's very nice for integration's sake. Because if I distribute secant into the numerator, so here in the denominator I have secant of x plus tangent of x, but in the numerator I get secant times secant is secant squared, and then secant times tangent gives me secant tangent. And this is with respect to x. This gives me a very, very nice u substitution. So to integrate this, we would say, well, let's let u be the denominator, where u is secant of x plus tangent of x. And then if I take the derivative of this, du, well, derivative of secant is secant tangent. Derivative of tangent is secant squared, and that's all a derivative with respect to x. And that's conveniently what we have in the numerator identically, secant tangent plus secant squared. So it's almost by some miracle that this works out, and we get the antiderivative of 1 over u du, which we can then integrate to give us natural log absolute value of u plus a constant c. And then we just have to back substitute. So I'll get back to the baby blue. And say here we get natural log absolute value of u is secant x plus tangent x, plus a constant c if we're just showing it as a generic antiderivative. Hey, so if you haven't seen this before, you can't really say that anymore because you just saw it now here first, that the antiderivative of secant is natural log of the absolute value of secant x plus tangent x, and plus our constant of integration. Now let's use this result, of course, with our bounded integral. So here I want natural log absolute value of secant of x plus tangent of x. I don't need the constant because I have a bounded integral, and this is from 0 to pi over 4. And I would like to evaluate this, so I want to plug in the upper bound, the lower bound, and subtract in order. Let me break away to where I have a bit more space to do that. So when I plug in my upper bound of pi over 4, I have natural log of secant of pi over 4 plus tangent of pi over 4. And then I want to subtract away from this what I get when I plug in 0 for x. So that's going to be natural log secant of 0 plus tangent of 0. And I'd like to go through and evaluate these pieces. Now remember, This is just made up of sines and cosines. Remember, tangent is sine over cosine, secant is 1 over cosine. So it might not be a bad idea just to go here to the side and say, well, what is sine of pi over 4? What is cosine of pi over 4? What is sine of 0? What is cosine of 0? Sine of pi over 4 is radical 2 divided by 2. Same with cosine of pi over 4. They're actually equal. Sine of 0 is 0. Cosine of 0 is 1. And so what we can say then is we could actually talk about tangent. So since tangent, well, let's go through these in order, I guess. I don't want to just keep yelling at the computer, yelling at you. Let's start plugging these things in. So we get natural log, absolute value. Secant of pi over 4 is 1 over cosine at pi over 4. So that's 1 over radical 2 over 2. Plus tangent at pi over 4, that's sine over cosine, which is radical 2 over radical 2 over 2. So we know what's going to happen there. Minus natural log absolute value. Secant at 0 is 1 over cosine at 0, so that's 1 over 1. Plus tangent at 0 is sine at 0 over cosine at 0, so that's 0 over 1. Let's say, well, what do we get here? Yes, natural log absolute value of 1 over radical 2 divided by 2 is going to flip the fraction, so we get 2 over radical 2, plus same thing on top, same thing on bottom, gives us 1, minus natural log of here we have 1 over 1 is 1, plus 0. And we can work through this just a little bit more. So we have natural log. I don't need the absolute value anymore if I see these things are positive values. So I have 2 over radical 2 plus 1, minus natural log of 1. Remember though, natural log of 1 is equal to 0. So this is gone. And I can rationalize the 2 over square root 2 just to make it look nicer. I could multiply by radical 2 over radical 2 just to that one term, just to clean that one up. Natural log of, now I'm going to have 2 square root 2 all divided by 2, then plus 1, then minus ln of 1 is 0. And maybe just one last step here, we can get rid of the 2 over 2, so we get natural log of square root of 2 plus 1 would be our arc length. Really cool example. I like this one a lot. Let's take a look at area of surface of revolution. Now, a couple important ideas to keep in mind, and this is where I always like to start, are these generic forms. If we're rotating our curve about the x-axis, the formula we want to use is the integral of 2 pi y ds. So if we're rotating about the x-axis, it's 2 pi y ds. Whereas if we're rotating about the y-axis, it's 2 pi x ds. And the ds refers to arc length. We have an integral with respect to arc length. And arc length doesn't care if it's with respect to x or with respect to y. So we could use those interchangeably. So I want you to keep that in mind, that we get some bit of choice here, and we want to think what would make the most sense in the context that we have with our problem. But I always like to start with the type of rotation, the generic formula, and then I like to look at the bounds, like I was saying in the arc length section that we just got done with. Let's see some examples. I want to find the exact area of the surface obtained by rotating the curve about the x-axis. As soon as I hear that, rotating about the x-axis, I'm already writing down the integral of 2 pi y ds. Then, what I like to do next is I like to look at the bounds. My bounds are from 2 to 4 on x. Since my bounds are bounds on x, I don't want to change that if I can avoid it. So I'm going to try to set this up as an integral with respect to x, which means that I want to try to set this up as the integral 2 pi y, but I want ds to be in terms of x. So that's going to be arc length. I want this to be dx, which means I want this to be square root of 1 plus, I want this to be a dy dx squared term. And we'll talk about what has to happen then with y, and then some generic bounds, because it should be a bounded integral. Okay, so we've already done a lot of work without even really looking at the contenders here. I want to find the exact area of the surface obtained by rotating the curve 9x equals y squared plus 36, and that's from 2 to 4 in the x direction, about the x-axis. Now, since I want to get everything in terms of x, I want x to be the variable that I'm integrating with respect to. That means I really want to try to solve this equation for y as a function of x. So here I can solve for y squared first. Y squared is going to be 9x minus 36. And then I can take the square root, and we can talk a bit about this. So here we're going to get y is equal to, when I take the square root, I'm going to actually factor a 9 out. That's 9 times parentheses x minus 4. Oop, and I got sort of a little stray glitch mark there, so let me fix it, because you're worth it. That's just x minus, we'll just do a regular 4 today. So I just factored the 9 out, but it's still 9x minus 36, and I took the square root. And technically, when we take the square root, we should really have this plus or minus sign when we introduce it ourselves. And then from here, we would say, well, I can clean this up a bit. So plus or minus, square root of 9 is 3, and then radical x minus 4. However, we don't need that negative square root. We don't need the non-principal square root. We only need the principal square root, or the positive root. So I'm going to say here that we just want y equals, and I'll explain why, 3 radical x minus 4. And it's because of the type of rotation that we're doing. So if I were to draw a quick sketch as to how just the principal square root looks, so here, let me get my axes. I guess I'll switch to a different color. If I were to just draw this principal square root, or just some generic square root function, that would be in quadrant 1, sort of looking like this. And I'm rotating about the x-axis. Now, when I rotate this about the x-axis, I'm already producing that non-principal square root in the rotation itself. So I don't want to include it, right? It's already going to be part of the show because of the type of rotation that I'm doing. I just want to sort of point that out here. So we'd say we're just safe then with that principal square root. I don't want the plus or minus sign. I hate to break it to you, but that's what we're going to be working with right now. So that's the situation that we have. Now that I have y, I also am going to need essentially all the tools that I need for arc length. So I have to find dy dx. I have to find the derivative here. So dy dx. And just a bit of chain rule. So I get 3 times, and then derivative stuff to the 1/2 gives me 1/2. Stuff to the negative 1/2. The inner function goes back in. The derivative of the inner function is just 1. So that works out nicely there. And here I'm just thinking about this as 3 times x minus 4 to the 1/2 power, and using chain rule to take the derivative. And I would want to rewrite this. You better believe it. dy dx, I would say this is 3 over 2 times, I'm going to bring this x minus 4 to the negative 1/2 in the denominator, give it that positive exponent, and then I'm going to turn it back into the square root notation. So this is my dy dx. Now we had a generic form that we were going to work with here. Let me just write that down. That was the integral from a to b of 2 pi y, and then the square root of 1 plus, I wanted dy dx squared, and I wanted the integral with respect to x. I want to start plugging in these pieces. I know the bounds on x are from 2 to 4. So the integral from 2 to 4 of 2 times pi times y, but this is a problem, right? I'm integrating with respect to x, so I don't really want y, or to leave it as y. Instead, I want to replace it with the function of x that it is. So what is y? Well, y is 3 radical x minus 4. So instead of y, I use 3 radical x minus 4. And then times the square root of 1 plus And I have dy dx right here as well, but I want to square it, so that's going to be 3 over 2 radical x minus 4 quantity squared. And then this is an integral with respect to x. So my setup's already ready to go. And let's see if we can clean this up a bit. Integral from 2 to 4. 2 times 3 gives me 6 pi radical x minus 4 times square root of 1 plus, if I square this, 3 times 3 gives me 9 on top, divided by 2 times 2 is 4, and in the bottom as well, radical x minus 4 times radical x minus 4 just gives me x minus 4. I do want to keep it in parentheses. Since I squared it, I got rid of the square root. The square root was sort of like its home, so I got to keep the family together by using the parentheses there. And then dx. We say, looks great, but what do I want to do next? With these square roots that I have, I really want to be using the product property of the radical, where we'd say square root of a times square root of b is equal to square root of a times b. So I want to write this all as one root function, and I want to multiply it out. So we'd say integral from 2 to 4, I have 6 pi, but then I'm going to want the square root of, and I want to multiply this in. And try to think of the x minus 4 as one term. I think it makes it just a little bit faster. So I would say I want, instead of the 2 square roots, I want 1 square root, and I want to multiply the contents together. So x minus 4 times 1 plus, and then x minus 4 times 9 over 4 times x minus 4 dx. And this is going to clean up really nicely. The integral from 2 to 4, 6 pi, square root of x minus 4 times 1 is x minus 4, plus, and then here the x minus 4's cancel, 1 on top, 1 on bottom, so I'm just left with 9/4. And I want to try to get, combine these like terms, get those constants together. So we'll say the integral from 2 to 4, 6 pi square root of, this is going to be, so we'll just go here, we'll say x minus 4 is really going to be 16/4 plus 9/4. So that's going to give me x and then minus 7/4. dx. Hey, looks really good. We want to integrate. This is really just a very small substitution. We'd say, well, we let u be x minus 7/4. We get a direct translation, du is dx. So we think of this as the integral. I have 6 pi, but otherwise the integral of square root of u du, which is the integral of u to the 1/2, which if we integrate, this is going to give us, du, it's going to give us u to the 3/2 divided by 3/2. Instead of dividing by 3/2, I want to multiply by 2/3. And then we want to back substitute. So thinking about that substitution, the u sub, we'd say here I get 6 pi, and then I get 2/3 stuff to the 3/2. And then back substituting on u, that should be an x minus 7/4 in there. And then bounded from 2 to 4. Just a quick idea as to how the integration would look. Now let's just see if we can go through this one the rest of the way. 6 divided by 3 gives me 2. 2 times 2 is 4, so we have 4 pi. And then from there I want to evaluate. So let me do the evaluation now. Plug in 4 for x, plug in 2 for x, and subtract in between. So that's 4 minus 7/4 to the 3/2. Minus, we have 2 minus 7/4 to the 3/2. Get a common denominator. So here 4 is 16/4 minus 7/4, looks kind of familiar, to the 3/2, minus 2 is 8/4 minus 7/4 to the 3/2. And we can keep going with this. So here we have 4 pi in front. 16/4 minus 7/4 is going to give us 9/4. And that's to the 3/2 power, minus 8/4 minus 7/4 is 1/4 to the 3/2 power. And then I can work through the fractional exponents as well. So 4 pi, I like to do the fraction part first so I can do square roots and then cube. Square root of 9 is 3, square root of 4 is 2, and I still have to do the numerator exponent, minus square root of 1 is 1, square root of 4 is 2, but I still have to cube. So we have 4 pi, 3 times 3 times 3 gives us 27, over 2 times 2 times 2 is 8, minus 1 times 1 times 1 is 1, over 8. So 4 pi, subtracting the fractions, we get 26 over 8. Almost, well here if I go ahead and reduce the 4 over 8, that's what I would like to do next. So I have pi, but then I have 26 divided by 2, which is going to give me 13 pi for this one. So not too bad. And we'll take a look at one more example, and then we're going to get on out of here. So I have the curve rotated about the y-axis. As soon as I hear that, I'm already writing. Rotated about the y-axis means I want the integral of 2 pi x ds. Now my bounds are given as bounds on x as well, which is good, makes things a bit easier, I think. Integral of 2 pi x, and then arc length wants to be square root of 1 plus, I want dy dx squared dx. So all of this should be with respect to x in this case. And since y is already solved as a function of x, I can jump in. So the curve I have is y equals 1/4 x squared minus 1/2 ln of x. If I want to find dy dx, let's say 1/4 comes along, derivative of x squared is 2x, minus 1/2 comes along, derivative of natural log of x is 1 over x, and I can clean up this derivative. We'll say, okay, dy dx then gives me a 1/2 x minus, this is really 1 over 2x, but I'm going to write it as 1/2 x to the minus 1. And for arc length, because I have to work with arc length for the area of surface of revolution, I want to square this derivative. So I'm going to want dy dx squared. So I want 1/2 x minus 1/2 x to the minus 1 times itself. And I want to FOIL this out. We say, sure, we can FOIL. 1/2 times 1/2 is 1/4. X times x is x squared. For the outer and inner terms, they should be the same. I get 1/2 times negative 1/2 gives me negative 1/4. But x times x to the minus 1 just cancels. And then I get another negative 1/4. And for the last term, negative times negative is positive. 1/2 times 1/2 is 1/4. X to the minus 1 times x to the minus 1 is x to the minus 2. And then I can go ahead and combine my constants and say, well, this is going to give me 1/4 x squared minus 1/2 plus 1/4 x to the minus 2. I do also want to add 1 to that square of the derivative. If we remember how arc length looks, we can already start preparing for that. So 1 plus dy dx squared. And so if I add 1 to it, I'm really just going to add it here to the constant. So I have my 1/4 x squared. When I add the 1, 1 plus negative 1/2 gives me positive 1/2, and then I can write the rest. And now I sort of have the pieces that I'm going to need to assemble my integral. So let's go ahead and start assembling that. We said that should be the integral of 2 pi x. I have bounds from 1 to 2. And we said it should be 2 pi x. And then our arc length, which is the square root of this expression that I just found. Right? We said square root of 1 plus dy dx squared with respect to x. Well, I just found 1 plus dy dx squared. So that's 1/4 x squared plus 1/2 plus 1/4 times x to the minus 2, and with respect to x. Looks really good. The integral doesn't, though. So this is one of those examples where we look at it and we say, doesn't look so great. If I'm going to have any success with integrating this, I'm really, really hoping that I can write this stuff under the square root as something squared. So we say try it. Don't just sit there wishing and hoping. We got to make some movement. Got to go for it. Are you going to go for it? We're going to go for it. Don't go crazy with this. Don't hurt your neck looking at it too much. Just try something. If I look at the first term, what could I square to get a 1/4 x squared? Well, I could do 1/2 times 1/2 to get the 1/4, and then x times x. So I feel good about that. Let's look at the last term. What could I square to get a 1/4 x to the minus 2? I could do 1/2 times 1/2 again to give me 1/4. I could do x to the minus 1 times x to the minus 1 to give me x to the minus 2. And since I want that middle term to be positive, I want a plus sign in between. And this is going to work. If I want to check the outer and the inner term, I can just do 2 times the product of these. That's 2 times 1/2 x times 1/2 x to the minus 1. 2 times 1/2 cancels. X times x to the minus 1 cancels, so I am just left with 1/2 for the outer and inner terms of FOIL. So works out perfectly. And now the square root and the square symbol can undo each other. We have the integral from 1 to 2 of 2 pi x times 1/2 x plus 1/2 x to the minus 1, which, since I'm done with my calculus, well, I'm actually not done with the calculus. I take that back. I have to integrate still. There's actually something nice that's going to happen. Let me rewrite this as a fraction right now. I'll say 1 over 2x. Because I want to point out something really nice that's going to happen with this in our next step. Because what I want to do is I want to distribute. I'm going to leave pi where it is. I don't want pi to move. But I'm going to distribute the 2 in. And you can probably see why. It's because the 2 is going to cancel with the 1/2. But I also want to distribute the x in. And when I do that, let's see what we get. This is going to be, I think, one of the nicest ones we're going to see all semester. We have the integral from 1 to 2. Here I'm left with pi in front. I bring the 2 in. 2 times 1/2 cancels in both cases. When I bring the x in, I get x times x is x squared. I still need my parentheses, x squared. And then x times 1 over x cancels. I'm just left with 1. And I still have the integration to do, so still the calculus, right? No, this simplifies so nicely. 2 times 1/2 is gone, bam. 2 times 1/2 is gone, bam. X times x, got an x squared, no problem. X times 1 over x, we'd say it's gone, bam, but really that means it's 1. Really just means that it's 1. X divided by x. And I can integrate this, no problem. I was ready to integrate this ever since Calc 1. If I integrate x squared, gives me x cubed over 3. If I integrate 1 with respect to x, gives me x. And this is from 1 to 2. Now I'm ready to evaluate. So pi is in front. I plug in 2 for x. I get 2 cubed over 3 plus 2. I want to subtract away from this. When I plug in 1 for x, I get 1 cubed over 3 plus 1. And then I can work through the rest of the evaluation. Here I have pi. 2 cubed is 8, so I have 8 over 3 plus 2. Bring the subtraction in. Minus 1 cubed is 1 over 3 minus 1. And just a bit left to go. I got pi in front. We'll combine the like. Well, they're all like constants, but we'll combine the fractions and then the integers. 8/3 minus 1/3 gives me 7/3. 2 minus 1 gives me 1. I'll get a common denominator now for my next trick. 7/3 plus 1 is really a funny way of saying 3/3. And then now I can add those like fractions. So I have pi times 10/3. Or just, since it is a final answer, I would probably write this really cute 10 pi over 3. Okay, and there we have it. Thank you so much for spending your time with me. If you're still watching the video, let me know in the comments beneath. Say, hey, I made it. I'm here, made it all the way through. Let me know if you're having a good time. But otherwise, no matter where you are, what you're doing, remember to keep learning, keep dreaming, and to always follow your heart. Go ahead, take a look at that homework, and I will see you next time. And until then, take care. All right, see ya.